So in your study for quantum physics, we have been here for quite a while. We looked at photoelectric effect, we look at electrons and how the behavior of an electron in its energy level causes us to understand conductivity and allow us to analyze orbitals and also the energy levels. But there's another thing about knowing the energy levels that allows us to actually really study X-ray. Now, the first X-ray, you know why X-ray is called the X-ray? Is because when it was discovered, when the scientist was playing through some scientific equipment and they found this ray, they didn't know what to call it. So unknown ray, then X-ray lo. Unknown X. So it is later on where this Röntgen, he managed to create X-ray properly, and he went and X-ray a photo of his wife's hand. So this is the very first, in inverted comma, I like how we throw shade. Okay, so this is the first X-ray of the human hand, and this is another X-ray of a human hand where this picture is much more better than this first one. So you can see the contrast and all that is adjusted. But if you look at this, something very interesting, this two X-ray diagram looks a bit different than what we are used to. Okay, so in this topic, we're going to look at how to make X-ray. The uses of X-ray, as you can see here, we're going to use it for medical imaging. We can use it to study crystals. We can use it for airport security to see if you bring any contraband with you. All right. And of course, this is not the first time you have encountered X-ray. You have heard about what an X-ray is when we talk about the electromagnetic spectrum. All right. And we're going to start off with the first part, which is what causes or how do we make X-ray. So this is an X-ray tube. Okay. So to produce X-ray, we need this device. Okay, so this is how it looks like in real life, but here I'm going to show you a drawing of it in 2D. Now, to produce X-ray, inside the X-ray tube, we are going to do this thing called bombard. Bombard is like rapid fire electron. So we're going to rapid fire the electron towards the heavy metal targets. I'm going to zoom in a bit, okay? So here you can see this is the electron tube. Okay, let's label some stuff. This EHT is probably what you're feeling right now since you are probably quite close to your trials. It's called extra high tension. But actually it is extra high voltage lah. So large accelerating potential. So this EHT actually is a large accelerating potential. To accelerate who? You want to bombard something, right? So it needs to be high speed. I just call this V lah, okay? So the electrons will be accelerated, but from where does this electron come from? Why suddenly got electron one? Well, you see, this is a filament. So we know when we heat the filament, there's this thing called the thermionic effect. Thermionic effect, where the electrons come out. Okay, so the electrons will come out from the metal surface. I'm going to maybe draw a zoom in diagram for you. Just give me a sec to label the filament. So this filament will get hot when we pass current through this. Okay, so we're going to pass some current through this particular circuit and the filament gets hot. So what happens when the filament gets hot? Okay, let me draw the filament, zoom in. So when the filament gets hot, in the metal surface, the electrons will get excited. And what do excited electrons do? They escape from the metal surface. Thermionic, ionic emission. This is not the photoelectric emission. This is the release or emission of electron from a hot metal surface. So we heat up the metal surface by current through the filament. So now the electron all come out now. They are like, hey, where to go? We are outside the filament, the heavy metal, the filament, and then we need to be accelerated and bombard the heavy metal target. Basically, I want to whack this heavy metal with a lot of fast-moving electrons. So the heavy metal is here. I want to allow a lot of electrons to collide. Bang, bang. The electrons to collide here. Okay, so this is why we need this extra high tension, large accelerating potential to accelerate the electron. So we're going to first think about it that way, and we'll write down what causes the production of X-ray. So if they say how is X-ray is produced, we will say we will bombard. It's the bombardment of metal targets with high-speed electrons. So let us look at what happens inside the metal target. All right, so now we zoom in into the heavy metal target. And the heavy metal target that we are using is called tungsten most of the time. Okay, these are just extra details. So this tungsten, this is the nucleus of your heavy metal. And we have these electrons that are incoming. So imagine the electron is coming, and then they are like high-speed electron being bombarded towards the nucleus of the heavy metal, or basically the atom of the heavy metal. That will be better. Okay, so this atom of the heavy metal has electrons all around it, and the electrons will slow down this high-speed electron because it has its own orbitals around here. It has its own electron cloud. They have their own electron cloud, and they don't like this high-speed electron. Excuse me, you high-speed electron, you are negatively charged, we are negatively charged. I don't think we can be friends. So what they will do is, instead of allowing this to collide, this one will be deflected this way. So now this is slowed down. But the kinetic energy needs to go somewhere. Okay, so this kinetic energy is released out as X-ray photon. And this was the X-ray photon that was picked up from. Okay, so we have this high-speed electron that we throw at the metal target, the tungsten target. We throw it, and this high-speed electron will be slowed down. And during this slowing down process, this high-speed electron will release X-ray photons of different wavelengths. Okay, because why? Number one, not all the incoming high-speed electron has the same speed. Number two, they don't approach at the same distance. So which means, based on your understanding of electric field, they will have different electric force. Then they will have different acceleration. So this is X-ray photon with a range of wavelengths. Okay, so we put that aside first. There's a range of wavelengths. And this X-ray beam will come out here. It will come out this way. And normally in the X-ray tube, we will have an X-ray window here. This is a window that sometimes we may or may not put a filter. Oftentimes we will, because this will allow us to adjust the amount of X-rays that come out. All right. So you may be thinking, what happens to this slow down electron? Where did it go? Don't forget we are bombarding. So bombard doesn't mean I send 3 electrons. Although I only draw 3 lines here. Bombard means I send many electrons. All the extra electron needs to go somewhere, right? So based on what you learned before in circuits, all the extra electron, nowhere to go. What do? We ground them. So here, the grounding here is to allow the excess electron to flow out. And this is important because you don't want this to store too much charge. So this is a safety precaution. So the copper anode, number 1, is grounded to allow excess charge to flow out. Number 2, this is also spin and cooled rapidly. So there has to be an in-house cooling system because this thing is going to get very hot very fast. Okay, so this is to prevent overheating. Because all these slow down high-speed electron, they still have kinetic energy, right? They will still disturb the heavy metal target. So the heavy metal target will become very, very hot. You don't want it to melt halfway. You do your experiment halfway. You take your X-ray image halfway. Then suddenly, GG, your X-ray tube melted. Is that going to happen to my laptop? I don't know. Anyway, to prevent overheating of the metal target, hashtag pray for my laptop. I think I say this too many times in too many videos already. Okay, so we spin it very quickly. This is to prevent overheating. slow down, the electron that slow down already doesn't mean that it doesn't have any energy. It will still disturb the particle. The tungsten metal will still become hot. All right. So what else? I think that's it. So the only thing I need to remind you is that this is high speed electron. Pew, pew, pew. Okay. So when we have this X-ray beam, right, what we do is we try to analyze this X-ray beam. Okay. We try to analyze and see what kind of picture or diagram that we have by plotting the intensity of the X-ray beam against wavelength. So we will get a graph that looks like this. And we call this the X-ray spectrum. Okay, so let's think about the X-ray spectrum first. For this X-ray spectrum, right, you will notice that there are two characteristics. Number one, you will see a continuous distribution, which is this curve that goes up and come down. It's kind of like a bell curve, but a bit lopsided. And then you will see these spiky lines here. So there are two characteristics that we need to talk about, and we need to explain what this graph represents. But in case you've forgotten what intensity is for a wave, this is power per unit area, which has something to do with the amount of energy that comes out. Because power is related to energy, and the energy that we care about here is energy of photon, which can be calculated using the equation of hc over lambda. Okay, so this tells me that the smaller the lambda, the greater the energy. Okay, so this intensity here depends on this, but also at the same time, you also have the number of photons. Number of X-ray photons. Okay, so number of X-ray photons here, it depends on how many photons that you have of this particular wavelength, lambda naught. And to make the understanding for this graph easier to understand, this intensity is only dependent on number of X-ray photon. If you think about it this way, your brain will not get stuck in some weird loop where you are uncertain now is frequency constant, is intensity constant. So this intensity here, to make your life easier, is the number of pings or the number of X-ray photons. So for lambda naught, this will have the least X-ray photon. In front of lambda dot, there is no X-ray photons. And after this, you can see the number increase to a maximum value and then decrease again. Okay, so right now, we will talk about this continuous distribution. The part that I'm highlighting here, it is continuous. All right, so to explain this continuous distribution, you need to think about the range of wavelengths that I mentioned just now. If you look at the drawing that I've given you here, you will see that this high-speed electron will slow down. But when it decelerates, it may not decelerate the same amount, because it depends on how close do they come between the atoms. Okay, so here it will slow down and we have a range of wavelengths. That explains why you have a continuous distribution of your wavelength. So we'll write that down first. Right, so they have a range of accelerations. I guess you could use range of speeds, but acceleration is the keyword that you're looking for because it will slow down. You can use deceleration, but hopefully by this point in time in your study in physics, you will understand that acceleration is change in velocity. So it can be slowing down, it can be speeding up. We will still stick to the term acceleration. So because the electron hitting the target metal has a range of accelerations, okay? And the point number 2, you can say that when is X-ray produced? Okay, so remember the X-ray will shoot out in that particular diagram. So we will say that X-ray photons are produced when the electron decelerates or accelerates or slows down. Okay, I think easier for the brain. Electron slows down, gets deflected. Okay, and finally number 3, since there is a range of acceleration, there will be a range, or there is a distribution, range distribution of the range of wavelength. All right. So normally if they ask you, they will ask you to explain this characteristic, which is these 3 points. Electrons hitting target metal, different acceleration. Because they have different acceleration and X-rays are produced during this acceleration, you will have a range of wavelengths. Right, besides the continuous distribution of wavelength, you will notice that there's a sharp cut off here, meaning anything that is after lambda naught don't have. All right, so this lambda naught has a special name. All these kind of special point must be named. You know, humans are like that. We got to name the special, unique things. All right, so this lambda naught is called a cut-off wavelength. So how do we explain this cut-off wavelength? We have to understand that this cut-off wavelength is minimum. So relate it back to the energy of the X-ray photon. So number one, we could say that this is a minimum wavelength. So indicating that the energy of the X-ray photon. So every time I mention the word photon in this particular subtopic, it's understood that it is X-ray. So the minimum wavelength corresponds to the maximum energy of X-ray photon. And just remember when we mention photon, it's about X-ray. So if this is the greatest energy, this means that the electron that was slowing down to give you its energy in the form of X-ray photon is giving you all its energy. So this one means that the high-speed electrons loses or stops in a single collision on the target metal. And because of this, all the kinetic in bracket, because you don't have to mention this, but all the energy is given to a single X-ray photon. So if you are asked to explain the existence of this cutoff wavelength, this means that this is the magical and very rare electron where when it collides with the metal surface or go close to the metal surface, it doesn't slow down, it stops entirely. Meaning this X-ray photon will be the biggest amount of energy, which means the wavelength is the shortest, based on the equation of the energy of a photon. All right, so we have already explained the wavelength distribution for the continuous one, which by the way, there's another name for this continuous wavelength distribution, which I find it quite cool. It's called the Bremsstrahlung. It's named after this German guy, and probably I'm not quite pronouncing it quite right, but this is also known as the breaking wavelength, or basically this is the German word. So whenever we say breaking or Bremsstrahlung, it means the same thing as the continuous distribution of wavelength. But in CIE, they just call this a continuous distribution. But in case you go to university and your physics professor mentioned this name, at least you know, oh hey, he is probably have some contribution in the continuous distribution. But the second thing we want to talk about is the spikes. You see all this spiky thing? What does this spikes mean? You will notice that this means that at certain wavelength, don't know how, don't know why, the intensity very high. So these are few wavelengths. So when scientists found these peaks, right, they were like, this is very curious. Why does this happen? Why? All right. So these are what we call the characteristic lines. Okay, so this is the emission or characteristic line spectrum. And they notice that for the same element, they will have the peaks exactly at the same places. No matter how much they change the speed of the electron or adjust the speed of the electron, you still get the same characteristic line spectrum. So immediately, right, they thought about the energy level, because another way for us to decide like how every single atom is unique and distinct is through their energy level transition. right? So this has something to do with the energy level transition, especially when the electrons bombard the target metal. Something is going on inside the orbitals of the target metal. Let's look at the nucleus and the orbitals of your tungsten or heavy metal target. Okay, so there are a few things happening here. I'm going to zoom in for you, and then you can see that in this nucleus, right, it's like chilling with all the electrons in the orbital. Again, this drawing is not the real orbitals, but we will draw something like this to help us understand. There are two types of electrons. First one is the yellow one that is inside the inner shell or the low energy level. Okay, and the second one is at the outer shell, which is the high energy level. If this diagram very unfamiliar, I'm not going to draw the energy level diagram that you are familiar with from the hydrogen atom spectrum. So here's a more familiar energy level diagram. And your high-speed electron is headed right towards this electron in the inner shell. Dot, dot, dot means many energy level I didn't draw, okay? So I just draw one in the outer orbits, the green color one. And the orange one is in the lower orbit. So if this high-speed electron pick out this orange, because it's like low energy when the high-speed electron come incoming, this one will be kicked out. Not here liao, vacancy. There's a vacancy here, an empty spot. Okay, you may be thinking, wouldn't there be some X-ray photon because the high-speed electron will also slow down? That's right. That will contribute to the continuous X-ray spectrum. But what I want to talk about is the line. Because you see there's a vacancy, there's an empty room. The green electron is like, hey, I have a more stable state to be in. If you do any form of chemistry, you will know the life goal of every single element, including you, is to be stable. What you study A-level? To be stable. So your future is guaranteed, or so they say. Anyway, this electron is going to transition down to the lower energy level. But when you transition to lower energy level, you lose energy, right? So there will be some energy that is released in the form of photon, and these are X-ray photons. These energy levels are discrete, okay? This means that the X-ray, so here, I'm going to zoom in a bit so you can see a bit clearly. So these X-ray photons, so this one goes to the lower energy level. Lower E level. This electron gets ejected, and finally, there is an X-ray photon. So this X-ray photon, due to orbital transition, is discrete, meaning there's only that transition possible because the energy levels are discrete. So that explains the line. Only certain values of lambda is only possible because only certain value of frequency and only certain level of type of photon is available to transit. Whereas the decelerating one can happen at a range. Speed is a continuous number, whereas the energy transition is discrete, which was the main idea that we talked about in the hydrogen spectrum analysis. So let's go back to the graph right? The characteristic line spectrum is due to the higher energy electron in the higher orbit transitioning to the lower energy. Because why can transition? Because the fast-moving high-speed electron knock out someone else. All right, knock out the electron. So now got empty space. So we're not going to write all of that. Okay, that is the short way of explaining this is the de-excitation. Right, so it's due to the de-excitation of orbital electron in the target metal. These orbits are discrete, so these values are also discrete. So you put the continuous distribution and the line spectrum together, you get this kind of, I like to call this the dinosaur graph because it looks like the back of a dinosaur. But that's maybe just me watching too much Jurassic Park. Anyway, what have we learned in this video? We have understood what is X-ray, basically, which is electromagnetic radiation at a certain window of frequencies. There are many usage for this, okay? But the important part or the important takeaway is you should know how it's being produced. So step one, I will heat up a filament. so that electron can come out first. We need the electron as raw material. Step 2, I will accelerate the electron using extra high tension or extra high voltage. So the electrons will collide with the tungsten metal at high speed. That high speed collision we like to call bombardment. Be a bit aggressive. We bombard the target metal such as tungsten with high speed electrons. During this bombardment, two things will happen. Number one, the electron could come close to the atom and get slowed down. In the process of being slowed down, it will release X-ray photon of a range of frequency and a range of wavelength. So this is how we got the continuous spectrum. Number two, it may strike jackpot and knock out one of the orbital electron. When you knock out one of the orbital electrons, some other electron will come and take its place. That will cause your characteristic lines on your spectrum. Okay. So other things to note would be that the copper anode has to be grounded and spin and cooled so that you want to prevent overheating. And number two, the existence of this cut-off wavelength, right? So we have this cut-off wavelength here because let's say there are very little, but there are still certain photons. The electrons, when collide, loses all its energy because we're talking about billions and billions of bombarding electron. Not one, not two, not 1,000, but Avogadro constant, okay? So this is why confirm we will have certain electrons that are close to or exactly the cut-off wavelength. So if you can explain these three phenomena or these three characteristics about the graph, which is the cut-off wavelength, continuous distribution, and emission, that will be the first understanding of what an X-ray is, how it's being produced. And in the next video, we are going to talk about how do we control this X-ray beam. Science of humanity, we want to be able to produce, study, and control this X-ray for medical purposes and for the benefit of mankind. All right, so I'll see you in that next video. Take care. Bye-bye.